Welcome back to the classroom. My name is Mr. Wong. Today we'll be looking at Module 5, Inquiry Question 2, which is on circular motion, and we'll be focusing on this particular dot point. So, the title is Circular Motion, Energy and Work. Our lesson intention is to investigate the work done by an object to execute some form of uniform circular motion. Your success criteria is your ability to analyze the energy changes as the object is undergoing that uniform circular motion. Your textbook reference is here if you need, and let's get started. So our journey so far in Inquiry 2, we've talked about uniform circular motion, the concept that an object will always move at the same tangential speed of its circular path. The reason why objects go in a circular path is because there is a net force that equates to what we know as the centripetal force. We also know that the centripetal force is not a real force, it is just a resultant force. We also looked at objects going on banked curves, and we found out there is a particular formula that can help express how fast the object should be moving in order so that it maintains its circular path without deviating into a larger radius. And we call that the design speed. Okay, so there's that. Okay, we've talked about, objects moving in a straight line motion. And I just want to give you a quick recap. Imagine we have a car that's moving directly straight. So in one straight line here, the net force experienced by the car here, assuming it's moving at a constant velocity, okay, so there is no acceleration towards the right, no acceleration towards the left. This is what we see here. It also has a balanced net force going down from our gravitational force down here, and also from our normal force going up here. Okay, so you can see how these two arrows are of the same length but in opposite directions. So Fg is my gravitational force, Fn is my normal force. This comes from the contact the object makes to the ground here. When these two add together, I get a net force of 0, which explains why, as the car is traveling, it's not sinking down, it's not going up on the road. Okay, so that's what we have. This gives us a nice explanation of where the object is moving. Now let's change our minds from rectilinear motion, which is a motion for a singular straight line, and let's apply that if an object was going in circular motion, say for our loop-the-loop example here, or when we are just trying to do a circular bend on a horizontal curved road, how differently would things be? The loop-the-loop will come later. Let's firstly look at something a little bit more simple. If we have a circular motion on a valley, so when you're driving downhill and then there's sort of this little dip and then you go back uphill, that's what we call a circular valley. Okay, now when the car is going down this valley, the centripetal acceleration is pointing up. So I'll just draw this out. There's that. The reason why it's going up is, as you can see at the bottom here, we have a circular path. So as the car is moving down here, all right, the net resultant force should guide it towards the center like we see, like so. Okay, now we can see a couple of things. Let's assume the person is at the very bottom of this motion. Let's just get rid of some of these marks here so we can see it more clearly. So our driver is at the very bottom of this dip and is still moving in this straight direction up. Now what we can tell is at the very bottom bit here, the driver will have a gravitational force. They will also have a normal force. And we also have a net force pulling it up. Now, let's assume we don't know the normal force. In a scenario like this, the normal force would be much larger than the gravitational force, right? The reason being is our net force of this car at the bottom of this dip is pointing up. So if we do the formula equations that we looked at before, net force is equal to gravitational force plus the normal force, and then we rearrange our formula around net force subtracted by normal force, you can see that the normal force in this case would be even larger, okay, even larger than the 1300 newtons. The reason why we can say this is because the gravitational force is in the opposite direction. So we could say this direction coming down here is also a negative direction. So 1300 minus 490, you can do the maths there. We'll have a normal force of 1790 newtons. So that's the amount of normal force being exerted by the ground onto our car up. And we also know your ability to feel your own weight is really much dependent on the type of contact you make to the surface. So if our normal force is much higher than our gravitational force in this period of time, we would actually feel a stronger weight force as we are going down this dip and going back up. So that kind of explains why when you go on a roller coaster ride and you're all the way down to the dip and just before you begin to rise back up, that kind of explains to why you feel like your weight force feels that much higher in that scenario there. Okay, so what if we are at the top of the hill? As you can see, there's a lot of values here, so just to keep things simple, just focus more on the vector arrows the two vector arrows, the two reds here, and our sort of, purple color here, or pinkish purple. All right, so in this scenario here, at the very top of our peak, the circle path goes like this. So our net force is going down towards the center here. Okay, down like so. What that means is our net force and our gravitational force is in the same direction. So what we should expect is as we go to the very top, the normal force would be smaller. Okay, would be much lower than the gravitational force. That meaning that your apparent weight force as you reach the top here is lower. So that kind of gives you that sensation when you ride a roller coaster just to the very peak and just before you're about to fall off, or fall down, sorry, not fall off. That explains why you feel a lot less weight as you are falling down, because the gravitational force, net force, are in the same direction, opposing that normal contact force. We can actually have a look using the numbers we have here. So my net force equals to my gravitational force plus my normal force. If I rearrange the equation, my normal force is equal to the net subtracted by gravity. So my net force is 80 subtracted by 490. So that gives us negative 410 newtons, which makes sense, right? So 410 is clearly smaller than 490. So that, from the mathematics, it shows to us why we feel less weight force as we reach the very top of that curly road. Okay. As you can see, there's some questions for you to do. I'll do a separate video that goes through how to do these calculations. What we're going to do in this video is more focusing on just the theory work, same as usual. Okay, so now we reach to the main component. So we now know what type of forces are acting on an object if it does some kind of vertical circular motion. Okay, so that's the example we have here. So now that we know the different forces, let's look at the energy considerations, and that is energy and work done. Just to refresh your memory, conservation of energy states that the total energy of the system can be added by the system or object's kinetic and potential energy. So kinetic energy here, potential energy here. When they add together, it should be 0. This 0 represents the concept of conservation. Okay, so that means that potential energy is lost. It becomes kinetic energy. If kinetic energy is lost, it becomes potential energy. And so that's why we have a 0 number at the end. Okay. If we somehow lost or gained energy, then it would no longer equal 0, and that would violate the conservation of energy. If we're looking at the example of, let's say, a loop-the-loop, we can use potential energy as gravitational potential, GPE. Okay, so if we're looking at changes of height of an object, we can substitute the equations to look like so. So this is the formula for kinetic energy, and this is the formula for gravitational potential energy. Again, same idea, they all add up to 0 because energy is conserved in that particular system. And that's only if we have a closed system. Alright, what about work done? When is work being done by or done on our system? Let me give you two scenarios here of how we actually express work done. So work done by the conventional formula can be expressed as the energy used to move an object in the same direction to its applied force. Okay, so W, work done, is equal to force and displacement. So if we look at where our car is, where it's being pushed, right, at this particular point, it's being pushed in that direction. If the motion of the force and the displacement are not parallel to each other, then we use cos theta to represent the angle between the force and the displacement. What this means is if the force applied to an object is perpendicular to where the object actually moves, so 90 degrees, then there is no work being done because you're not actually moving the object parallel to where you apply the force. We'll go into that a little bit more later on. Another way to interpret work done is the change in kinetic energy or the potential energy, in this case with our roller skater, gravitational potential. We can express it like so. Now, you might wonder why gravitational potential is negative here, given that energy is a scalar quantity, so there's no direction. Well, the reason why it's negative is to represent that these two are being transformed into another. How is it being transformed? That's because work is being done by or from on the system. If we're looking at the skateboarder going up and down, you can see that the total energy has never changed in this scenario. What has changed is the kinetic and potential energy. So at the very top of this peak, we have maximum gravitational potential. As the skateboarder comes down, work is being done by gravity to push our skateboarder down in this particular direction. As work is being done on the skateboarder, they gain kinetic energy. So just think of in those kind of scenarios, is work being done on or by our system? Another way we can sort of picture work done is if we have a look at this. We said that work is done if the object we're moving is parallel to the direction we are applying that force to move it. So if we're lifting a box directly up, then that represents work being done. Let's look at the scenario B here. So I've picked up my box, I'm holding it up, so I'm lifting it up, and I'm walking, perpendicular to the direction I'm holding the box. In this case, no work is being done. The reason why no work is being done is the displacement or the direction of motion is perpendicular to the force applied to hold the box up. So I'm not actually moving the box because of the force I'm applying, and the box is not moving in the direction I'm applying the force. So that's why there's no work being done. Okay, so what we can conclude is for a scenario like this, where we're performing circular motion horizontally, there is no change in potential or kinetic energy. So as you can see, when I'm just swinging this plane on a string directly horizontally, there is no change in height, so there is no change in height. If there's no change in height, that means there's no change in gravitational potential. If there's no change in gravitational potential, there is no change in kinetic energy, which means there is no work being done on this system in this scenario here. Okay. We can also look at it as a top end motion. So if we're looking at it from the top or any form of circular motion, we can actually tell there is no work being done here. So if an object is just performing a direct circular motion, you can actually see when an object's undergoing circular motion, that's where it's traveling. Okay, that's the force that's being applied. Again, force and displacement are perpendicular to each other. So what we can say is, if an object is going through circular motion, in this case here, on a directly horizontal plane, then work done is 0. And I need to make that very clear. That's only if there is, if we're on a horizontal plane. Okay, so I guess what you can kind of gauge from what we're talking about here, if we just talked about the horizontal plane, now we talk about what if the circular motion is vertical. What's the scenario there? Well, there is changes now if we are looking at circular motion in the vertical component. So let's have a look. So energy changes for circular motion. Our car at the bottom here, it's starting to move up this hill. Now, assuming this is our 0 point, so height is 0 here, we have 0 potential energy, and we have maximum kinetic energy possible to go up. Okay? As we go up this hill here, we can expect that gravitational potential is increasing, and we are seeing a decrease in kinetic energy because height is being changed. All right? The change in height is increasing. So what can we say in that case there? We can say that work is being done by the car to move up the mountain. okay, or work is being done to move against gravity. Okay, so in this case here, work done to move against gravity. What about when we're up here? Gravitational potential is maximum. Kinetic energy, assuming that once we reach the peak, the object temporarily stops moving, then, you know, that's the conversion we have there. As the trolley goes down the hill, though, work is now being done. So work by gravity to push or pull car down. Okay, so work is now being done by gravity to push our car down. As that happens, the potential energy is decreasing and the kinetic energy is now increasing again. Once the car goes back to the bottom of the hill, we get, you know, maximum kinetic energy and zero potential energy, if we are assuming this is our 0 point here. So just keep that in mind. To express the equations to describe this motion, okay, we have the total energy here and the final total here. Just remember, when you're doing any laws of conservation of energy, there's always a kinetic energy component plus a gravitational potential energy component, and then make sure you do that as well when you look at the next motion that you want to analyze. So we'll look at some calculations that uses the consideration of conservation of energy as an object is moving up and down a slope, and we can look at what that teaches us. So this is the problem we'll look into, but like we said again, that'll be in a separate video, so please watch that one if you want to know how to do this particular question. Alright, and so that concludes our theory component of energy changes in circular motion. If you found this video useful, give it a like, subscribe, and please have a look at the problems for these type of questions in our next video.